Today you'll be hearing Accelerating Innovation with Additive Manufacturing by Carl Douglas and Brian Douglas. Carl and Brian are the co-founders of DI Labs. DI Labs helps companies gain a competitive advantage to take a new approach to their product development and manufacturing process. Carl has 20 years of experience as an engineer. He has unique depth of knowledge and experience in leading new product development manufacturing optimization. Brian is a product designer and inventor with nearly 15 years of experience in precision electromechanical system design, diagnostics, and repair. With that said, I'm going to go ahead and pass this over to Carl so that he can start the presentation.
Thanks, Robin. Good afternoon, everyone. Thanks for joining us on this lovely Thursday, wherever you all may be. So as Robin said, we're going to share with you a little bit about our experiences and technology with additive manufacturing. And so the objective with our talk today is a couple things. We want to share with you the experiences that we've had with the technology that we operate. We want to be able to spark ideas and questions to help you accelerate your innovation and then ultimately help you create a competitive advantage for your business. As Robin said, this is something that's really important for us. It's what we do within our business and what we strive to do for our customers. It's all about getting there faster and getting an advantage against your competition. So that's what we'll talk about today. And before we get into that, I think it's good to share a little bit about our company to provide some context. And the foundation for our company is really innovation and product management. So when we started our business, this is what we focused on, and it's what we leverage additive manufacturing to do today. Along with that service, we provide product development and design services, which is less comprehensive, and then additive consulting. So essentially we help other companies bring on additive technologies, a great deal of experience in the workflow and process. So we help other customers bring on new technologies. So we use those capabilities to produce functional prototypes. These are things like 1Z, 2Z type parts, maybe up to 10 prototypes, and they're generally used for look, feel, or function to validate a design before going into production. In addition to that, we've got these things we call complex prototypes. We've got one in the presentation today, and it's something that it's a prototype that can't be produced as a single part, or it's extremely complicated. And we've got something neat to share today. And then finally, we use those capabilities to run full production. So we've got a couple of examples that we'll share today where we'll produce parts in the tens of thousands on our additive equipment and use our equipment in place of traditional manufacturing like injection molding, for example. So those are the building blocks for our business. And sure, I'll share a little bit about our history. So Brian and I founded our company in 2013. We're geeks, we're gearheads. So we founded our company as a product development firm. And the very first thing that we tackled was the redesign of print heads for fused filament fabrication machines. One of the challenges that we faced was we needed to be able to do prototyping to serve our customers' needs, but we needed to be able to do it significantly faster than the technology on the marketplace would allow us to. So we essentially developed a printhead system that was 2 to 4 times faster than anything else on the market. And we did that for ourselves, for our in-house needs, and we found that the market also needed that technology. So we ultimately licensed and supplied that hardware technology to printer manufacturers. And I think that's pretty important for us to share, simply because we've been deep into the thick of it. And we recognize the need for speed, the need to get to the market faster and capture the opportunities, again, before your competitors do. So along with the development of that technology, we've also been developing products over the last several years. And up until 2017, we were using the FDM technology that we had developed along with SLA to provide prototypes to our customers. We also did some outsourcing to other service bureaus, but what we realized was that either the quality wasn't there or the speed for us wasn't there. So in 2017, we made our first major expansion with additive manufacturing, and we purchased an HP multi-jet fusion machine. We are proud to say that we were the first in the state of Minnesota to have this machine, and it was necessary for us to be able to provide quicker response time to our customers, as well as greater volume capacity. So we purchased that at the end of 2017. And then about a year later, we doubled our capacity and brought on another 4,200. And since then, we've continued to expand our technologies and our technology portfolio to serve our customers' needs. And essentially the way it works is our customers will bring us a project. If we don't have the capabilities to serve the need for that project, then we'll make the investment in the technology to be able to do that. We love to solve problems. So looking at our technologies from a portfolio standpoint, we offer several different technologies. We operate the multi-jet fusion machines, both in the grayscale as well as the full color. We've brought on the carbon DLS technology, which was a recent move. And then we've got the Markforged machines as well. So we are able to print metal on the Markforged Metal X, and then composite materials on the Markforged composite machines. And then in addition to that, we've got the standard FDM type technology for ABS and PLA. And then we'll got a special machine that we run PEEK and Ultem and the engineered materials on. And then finally, we operate SLA. And then we get ourselves into some pretty advanced finishing technologies. So things like nickel plating or auto body level painting or chemical processing of parts to provide smooth sealed surfaces. So those are all things that we bring online to solve needs that our customers have for the finished products that we produce. And then just a little bit more about us. As I've shared, we're experienced product developers. We are family owned. So the three of us brothers are shown here on the screen. We're not the only ones in the business, thankfully, but we are all engineers, and we're driven to solve problems, and we're driven to help you accelerate your innovation, to give yourselves competitive advantages. So what does that mean, competitive advantage, and how do we use additive to provide that? The way that we think about it is in terms of the product life cycle. And I know that most of the folks on the webinar have been familiar with this type of graph. We added the development stage to this life cycle chart. Essentially, we've got the development stage, introduction, where the product gets introduced to the market and you start to build sales growth. And then you've got sales growth ramp up, which leads into a mature product line. And then ultimately at some point, that product line will mature and it'll end up declining in terms of demand from the marketplace. Well, we use additive manufacturing in each of these stages today. In terms of development, I think we're all familiar with using prototypes for development activities. It's been common for decades. We're also using additive manufacturing for the initial production. So thinking about in terms of offsetting risk and getting to the market sooner, we'll use, and we'll share some examples where we use our additive manufacturing equipment to bring on products to the market, get customer insights earlier and more often, so that we can sense what failures may exist before we go all in. And then going through the growth phase, we'll use additive manufacturing in terms of a bridge solution. So where we start to get to that volume demand where additive manufacturing may not have the capacity, we'll use additive to get us to the place where we can use injection molding. So we'll consider that as a bridge production tool. And then in the mature stages, we'll use additive in terms of jigs and fixtures. So it's really to help aid in the production of products using traditional technologies like additive manufacturing or subtractive manufacturing. And then finally, in the decline stage, we're using additive for on-demand repair supply. Rather than having extensive inventories of parts for products that are obsolete or out of date, we're using additive to basically serve as an on-demand supply chain. As parts break, we're able to respond quickly with production, which saves extensively in terms of cost of inventory. So from a real high level, this is how we're leveraging additive manufacturing. The industries that we're using additive in to solve these problems are everything that we've listed here on the screen, from industrial to automotive, aerospace, all the way down to consumer goods. This is just a small snapshot. As you can imagine, within each of these verticals, there's sub-segments that we serve as well. For the talk today, I'm really focused on these 4 segments. Each of the examples that we have today can be applied to all the segments shown on the screen, but primarily focused on these highlighted sessions. And then finally, all of the examples that we have will at one point or another encompass the entire product lifecycle from cradle to grave. And then as we go through each of the product examples, we'll highlight where they serve the life cycle. So case studies. We're sharing case studies, and we're sharing it in a format where it's a 2-step approach. First, I'll share with you the case study itself. I'll showcase how we applied additive manufacturing to solve a problem. I'll share what the results were, and then where in the life cycle that solution took place. And then we'll go behind the scenes a bit, and then share how the product or solution was made. Basically, how we did what we did. We'll share some tricks and secrets and packing configurations, as well as some special considerations that we had to take place in order to solve the problem. And as we go through this, I've got 5 or 6 different examples. What I would encourage everybody to do is, as you've got questions, raise your hand digitally, of course, or ask the question, and then we'll answer, do our best to answer those questions as we're going through the presentation. But please ask them as you have them. Okay. So the first example here is a full-scale prototype. This was a challenge that our customer brought us. It's a customer in the aerospace market, and they asked us to develop for them or produce for them a full-scale fuselage prototype for a new product a new airplane that they designed. They were going to do cockpit install and pilot testing with that structure. So the solution for that, we produced for them a 10 by 4.5 foot long fuselage in about 4 weeks from the time that they provided us with their fuselage design. We maintained the design wall thickness for their structure, which is about 300 thousandths thick. The body was comprised of interlocking panels and ultimately had an auto body style finish. So this is an example of what that vehicle looked like. This is not the exact product that we produced for them, but it's one that we've done for ourselves to demonstrate the capabilities. Now this fuselage, as you can see, it looks seamless on the screen. It was produced with about 130 panels, and there's two halves to this. We're showing the auto finished half on this side, and then the other half is unfinished. And this particular model was about 8 feet long. And the stage of the life cycle that we supported with this project was the tail end of the development stage to validate the design. And then it's been used to ramp up the sales and provide visuals for potential customers to allow them to see the aircraft before the mold and finished product was on the showroom floor. So this is a great example of where you can have a full-size prototype to have the potential customers basically develop pre-sales with them. So then the question is, how did we do it? So that particular model was comprised of over 130 panels. That's pretty tricky because the panels are thin. They all have to lock together. You can imagine it's like a three-dimensional jigsaw puzzle. So we had to design the panels to minimize or eliminate warping and dimensional change. We designed the pack to optimize the thermal management so that we could produce the body panels in fast and volume without having distortion. And then finally, to be able to maintain the outer surface of the skin. So this floating image here on the screen shows one of the packs that we had for the panels. And as you can see in here, there's maybe 10 or so panels in this pack. There's also some other parts in this file here that we ran along with this particular project. The entire fuselage was produced with a nylon PA12. So this virtual pack here shows what would come out of the HP multi-jet fusion, and it would have come out in nylon 12. The print time for a pack like this would have been probably about 14 to 16 hours. And because these panels are so thin, we cooled them over an extended period of time, something like 30 to 40 hours. So you can imagine as we were producing this fuselage body, we had 130 some odd panels, 10 to 13 panels per build. It took us about 10 builds to produce. So that kind of gives a snapshot of what that looked like from a process flow standpoint. And then this shows a partial assembly here in these photos of assembling the nose cone for that aircraft. We're also sharing an internal image of the nose cone. You can see that there's some unique geometries on the surface, some rectangular pockets. We ended up developing our own joining system for each of these panels, and then a joining tool to be able to join those panels together and have them be structurally sound. So those are just some tricks of the trade for bringing together a large structure like this. Alrighty, so we'll move on then to the next case study. We'll change gears here quite literally. So this was a manufacturing process adapter that was used for a customer that had developed a new product. It was a plastic tubing product, and they were challenged because the new product was different enough from their current tubing that the downstream processing equipment they had wasn't compatible with the new product. So they brought us the challenge of adapting the existing equipment to the new product and do so in a very short period of time. So as you can imagine, the product was being produced. They had this secondary process where they needed to modify that product and they needed to be able to get it out to customers. So time was of the essence. They brought us this challenge, and what we did was we essentially 3D printed adapter sleeves out of nylon PA12 and had them fit over an existing aluminum machined hub, essentially. So we adapted the existing technology for the new products. By doing that, we saved about six-figure capital expenditure. We prevented about a six-figure capital expenditure because they didn't need to make the new aluminum hubs. And on top of the expense savings, there was a time savings of about over 12 weeks. The reason for that was the aluminum hubs took something like 12 to 16 weeks to machine, and that would have prevented the new product from going to market in its final form. So in about a week and a half's time, we were able to reverse engineer the hubs and then 3D print these nylon sleeves to fit over them. And this project satisfied nearly all stages of the product life cycle for this customer, from the introduction to growth, and it has the ability to serve through the entire lifetime of the product in terms of manufacturing. In this case, the nylon sleeves may ultimately be phased out in lieu of aluminum hubs, but they do have the performance and strength to last the lifetime of the new product. So looking at this from a process and manufacturing standpoint for 3D printing, the process workflow for us was to scan the existing aluminum hubs. After that scan, we produced a prototype so that we could have something to fit the new sleeves to. And then we transitioned into production. So this rotating image here on the right shows 6 or 8 different sleeves that are in a virtual build. So for every one of the HP runs, we would have had about 8 sleeves that came out of a production. And this is how the parts would have been packed in the build. I just want to make sure I'm getting the questions here. Okay, so we've got a question that is, how durable is this printed sleeve, and can it be used long-term on a production line? That's a really good question. We found that these sleeves, after they were operated for well over a year, that the sleeves were showed a little bit of wear resistance, but it was only in discoloration, it wasn't in thickness. So this particular solution's still in place today, and it's still serving this application. We found the sleeves to be quite robust, and because they're being complemented with the aluminum hubs, there is really little extreme force that's being placed on the sleeves. So it turns out to be a great solution where you can combine subtractive manufacturing along with additive to solve challenging problems, and do so much faster and at a much lower cost than using just traditional subtractive manufacturing. All right, so we're going to transition now. We're going to change gears again into an example of a project where there was a new market introduction. We had a customer that came to us and they wanted to launch a new watertight threaded valve body. It was a part of a new piece of equipment that they had, that they weren't sure how big the market would be for this particular valve body, so they were hesitant to invest in injection molding. They needed to be able to assess the market, but that would require more than just 1 or 2 parts. So they came to us and asked us if we could help them finalize the design for additive manufacturing and produce these parts in low volume. The kicker was, of course, they needed them fast. They were at the place where they had the design nearly finalized, and the product was going to market that this valve body would be attached to. So time was of the essence. We ended up taking this design, modifying it, and delivering it in about a week and a half. And we used it to satisfy the introduction and growth phase of their product life cycle. So the images here show the valve bodies, which we produced in nylon, the PA12, and they did have the threads built in. That was a requirement for the customer, that the threads would be built in just as they would be with the injection molded parts, and the threads needed to be watertight. So this is something that we had done testing on and validated before we went into production. So looking at this from a behind the scenes standpoint, how did we get away with producing these and having them be functional? It was really important and necessary to have the threads that were functional and high performing. So we had done some testing before going into full production to make sure that we were able to consistently produce those threads and have the dimensional accuracy necessary for water tightness. We ended up developing a build pack design to optimize the output in terms of production volume, as well as part accuracy. And then the second component of that was streamlining the post-processing to remove the powder and get the parts so that they appeared to be nearly injection molded for our customer. And this rotating matrix is the basically part of the build pack that we have produced the parts in. Anytime we go through a project where we're transitioning from a prototype type stage to a full production, it's critical for us to be able to assess the build pack layout and make sure that it doesn't have a negative impact on the print accuracy and the consistency of parts from one part to the next. One of the things about sintered powder printing is that it's a lot like injection molding in terms of the thermal characteristics. So with injection molding, if you've got parts that have thick and thin sections, you can run the risk of warping or dimensional accuracy problems. And we face the same things with additive manufacturing, especially with the sintering process. So it's really critical as we pack builds, and for those that operate equipment, it's the same. We need to pack builds to make sure that we don't have hot zones and then adjacent to cold zones in the build. And those types of thermal differences can create dimensional inaccuracies. I'm going to check the questions here. So we've got a question that's asking, were these parts designed for air or water, and does it seal? So these parts were designed for water. They did seal. We had done some testing in-house. Most of the parts we did not chase the threads on, so the threads came out of the machine, parts went through the post-processing, and they were functional from that point on with the fittings that the customer had as part of their injection molded assemblies. All righty, thanks for these questions. They're good. Okay, switching gears yet again. This was an interesting project. So this was a customer that was developing a high performance automotive solution. They were essentially applying a supercharger to an existing inline 6 motor that wasn't designed to be supercharged. They weren't quite sure what the market size would be for their system, and they needed to be able to dyno tune their setup. So rather than going into a cast aluminum manifold, they came to us. We worked with them to essentially print their intake manifold. We printed it with glass bead reinforced nylon, and we worked with them to ensure that the design was capable of withstanding over 10 psi of pressure for the temperatures that it would be operating under. And again, the kicker, there's always a kicker, and the kicker in this case was that they needed to get the manifold on the car ASAP, basically as soon as possible. And we were able to reconfigure this manifold for Additive and deliver it to them within about a week. So this this bottom image shows the manifold close-up view of the manifold installed on their setup and their engine. It's kind of interesting because there's a couple of 3D printed parts on here. You can see that the manifold is black. It's got the fittings in it, supercharger that's mounted on it, and on the back end of the supercharger, there's another elbow that's also printed out of nylon. So there were several parts of this system that were all printed out of the nylon. This is an interesting project that is still ongoing. We used Additive to support them in the final phase of the development, along with the introduction and growth. We're working with them to understand whether or not this is feasible from an economic standpoint for full production. Depending on the volumes that they're producing, this may very well be a viable resource. For those that have looked under their hood in the last 5 to 7 years or so, I'm sure you've seen that there's a whole lot more plastic parts that are used for critical components of the engine, essentially on the intake side. So the materials that we're running for this manifold are not unlike what's being used by a lot of the OEM manufacturers for their underhood systems. So I just got a question. This is a good one. I'm glad you asked it. So the question is, are we able to thread plastic? And you'll see here, go back one slide. You'll see here on this image that stopped that there's a couple of brass fittings on the underside portion of this manifold. We had a couple of different options for the hardware connection. Either we could have threaded in the hardware, or we could have used brass inserts. And in this case, we decided the brass inserts would be a better solution. So these two areas underneath the manifold are essentially brass inserts, which are used for the support structure for the manifold and supercharger. And a situation like this, the inserts are a much better solution than either printing the threads in the part or tapping them after the fact. This turns out to be a great solution where we essentially heat stake the brass inserts right into the manifold.
Hey, Carl, I have a question that just came in as well. It's from Sam, and he's asking about the surface finish. Is it easy to control the surface finish on a plastic part?
Yeah, that's a great question. So Sam, you may have picked up on the difference in the image on the top of the screen to the image that's on the bottom. So the image that's on the bottom is a part that came out of our machine, and we essentially mechanically smoothed it. That's a form of tumbling. And we did that because we wanted to be able to have the smoothest finish possible. And then the surface finish that's on the top is a chemically smoothed part, which is basically smoothness taken to the next level. And we are able to control the smoothness of the parts to a certain degree with the printing process itself. And then we've got extra levels of post-processing that we can apply depending on what the customer requirements are. Generally speaking, you're probably looking at a smoothness, an RA smoothness of the glass bead parts on the order of probably about a 9 micron. When you do a tumbling, apply tumbling as a finishing method, you're probably going to be like in the 8 or 8.5 micron range. And then using chemical surfacing, you're probably going to be down in the 1.5 to 2 micron range. So there are tricks to help control the smoothness of the surface finishes.
Carl, thanks for that. It looks like he added another question about how controllable is that process? Is it controllable and repeatable?
It is. It is. There's probably a longer answer to that than just there is. We'd be happy to work with you, Sam, if you've got a particular project where you're trying to find a solution with a great deal of consistency on the smoothness. We've got some applications where we're probably within maybe a micron of consistency on RA value for smoothness. And it really depends on the application and the type of part and the geometry. One of the inherent characteristics of printing with a powder is that generally the top side of the part is going to be rougher than the bottom side. So what we'll do is that we'll orient parts to make sure that we've got the beauty face or the smooth face more smooth than the faces that don't need to be as smooth. Is there any more follow-up there, Robin?
That's all I have, Carl. Thanks. Anybody, if you have more interest in that, we can always address that towards the end of this webinar. Thanks, Carl.
Yeah. Thank you, Sam, for the question. Great question. Okay, so this one's pretty neat. So this shows how the manifold was essentially produced. The manifold was larger than the build volume of the HP machine. So what we did is we basically sliced it into two parts and built in a mechanical joint so that when we connected the parts back together, they'd be watertight and be able to withstand the pressure that they were subject to. You can see a number of other parts in this screen here. We did not change the build that we ran for this particular job. So you're seeing a typical job in the day of the life of a printer. Typically when we produce parts like this, in an effort to help maximize the thermal consistency within the build, we'll put other parts in the free space and make sure that we don't have extreme hot spots and cold spots. This is also part of the production process to make sure that we are using as much of the build volume as possible. And in this case, we did use an adhesive to connect the parts together. It was a two-fold connection, so the joint was designed so that it became positively engaged when it was assembled. And then in addition to that, we had pockets where we put in adhesive to ensure that the joint would remain permanently affixed. All right. So moving along to a project that we used additive in lieu of injection molding. This customer brought us kind of an interesting project. This is not to scale, but they brought us a part that they needed to be able to produce tens of thousands of quickly, and they needed them to be high precision. We worked with them pretty closely to understand the requirements for their finished parts in terms of strength and dimensions. And then we developed a manufacturing process tailored to this particular part so that we could produce it in volume. They placed an order with us one day and they needed thousands of parts within a few days. So it was imperative for us to be able to rapidly turn this around and be able to do so with the type of quality and dimensional accuracy that they demanded. So we were producing thousands of parts per day. This image here shows what the parts look like in real life. Kind of gives a sense of the scale. So they're fairly small parts. This was an early prototype run that we had done, and you can see that we had some printed in chain links, if you will, that connected the parts together. We designed those into the parts to make them easier to handle and manage through the post-processing. And for this particular customer, they had considered injection molding the parts. The challenge for them is that they had some unique features in terms of a channel that went through the part here. And it was too challenging injection mold, and on top of it, they needed, they were at the 11th hour. They needed to be able to get parts out as quickly as possible so that they didn't slow down their production operation. So this was a perfect example of where Additive was able to deliver quickly and in the volume that they needed of tens of thousands of parts within a short period of time. So looking at this from a manufacturing standpoint, we did have some challenges. The biggest was the powder removal from the internal channel and the handling during post-processing, especially with such a great deal of volume. So it's kind of neat. We built in a channel cleaner. So you could picture this as like a built-in pipe cleaner that was designed right into the part and produced as part of the production. And then the other thing that we did to help improve handling is that we printed these in batches of 5, so that when you pulled a batch out, you knew you had 5 parts, and it was easier to manage the removal of the built-in pipe cleaner, as well as the post-processing and cleaning of the channels. So this image that's rotating shows what part of the pack would have looked like. This was just one layer, and it shows just a small layer of what was produced within one of our machines.
Hey, Carl, we have another
Yes.
question that just came in, and it's a question that it's asked: how repeatable is the HP technology, and how do you verify accuracy?
Yeah, that's a great question. So it's like really like any additive or manufacturing or any manufacturing technology, there's a specific art and skill set required in order to maintain dimensional accuracy. So if we were to put parts in our machine and not be conscientious of the pack density or the orientation or the cooling rate, we would have a great deal of variability. So when we produce jobs like this, we'll produce them so that we have consistent pack density and consistent part orientation after we validate the initial dimensions. And we've found that we're able to maintain extraordinarily tight tolerances on the order of a few, plus or minus a few thousandths. That's geometry dependent, of course, but we're able to maintain very tight tolerances near that of injection molding in volume, but it requires us to be very conscientious of the production and cooling processes.
Thanks for that. And I guess another question has also been added: what is the largest volume of one particular part that you've printed?
Boy, that's a good question. We're probably in the neighborhood of maybe 100, probably right around 100,000 parts of volume of a single component. This was probably among one of the larger projects that we've done in one fell swoop. So this was one single order, and it was tens of thousands of parts. And we're seeing more and more of that, where additive is being used for extraordinarily high volumes of production. If we were asked back in 2017 when we purchased our first HP, if we could see ourselves producing parts at that order, I'm not sure that we would have said we could, but after we've understood the technology and how to leverage the output, 100,000 is definitely not the ceiling. As with any production technology, producing the parts is only part of the equation. It's the post-processing of the parts, the cleaning, the handling, the dimensional measurements that can be a bottleneck. So those are areas where it's really, really critical to optimize that leg of the process to make sure it's not a bottleneck.
It seems that we've hit a pretty interesting topic here. I have another question asking about what's easier for you to print, smaller parts or larger parts on the HP technology?
Easier is an interesting question. There really isn't one that's necessarily harder than another. Because of the build volume of the machine, think about it about like a foot cubed. It's a little bit larger than that, but think about it of a foot cubed. The larger the parts become in that build volume, the more costly they become. So we found that from a production standpoint, smaller parts tend to be, we're able to run them at higher volumes and be economically competitive. As the parts get larger, that can be a little bit more challenging from a cost structure standpoint. But there really isn't, it's really not harder or easier from a manufacturing standpoint.
Perfect. Thanks, Carl. That's all I had.
So another great question. Do you have any additive materials that can be used directly in the human body for medical applications? The short answer is yes. The long answer is that's a really nuanced and very specific area. I'd be definitely interested in talking more about that with you, Rob. The short answer is yes, we'd like to talk about that. Any other questions before we move along? We're going to stay on the same project on this slide. This was kind of an interesting process for us. So as we continue to produce those small parts, we found ourselves optimizing the process. And I wanted to share this with you all today. This little part here on the screen is a jig and a fixture that we designed to clean the channels of those parts. This was printed on the Mark Forge, so it's a reinforced nylon 6, and it's an assembly that has some action to it. So I'll play a short video here. So we designed that system so that it had nested pipe cleaners in it, and when you press down the trigger, it would essentially insert those pipe cleaners into the channels of the part. And I've got another video here that shows that system actually cleaning out a bunch of 5 parts. So this was a prototype fixture that we developed. There was a production version that was a little bit different than this design, but they were all 3D printed. And it just goes to show how you can leverage additive manufacturing to be extremely responsive to help either streamline a process when you get into production or reduce time. And we found this to be extraordinarily valuable for that leg of the project, as we were probably, so we got to the 25% mark. This was something that we implemented. And yes, we did hire a Seinfeld hand model for that, in case those were wondering. There's beautiful hands, beautiful hands.
I was just going to ask you that question, Carl.
Okay, moving along. This is another project that was pretty interesting. So this was an Aeroponics optimization and production project. A customer came to us that was doing aeroponics growth of produce, and they wanted to be able to go full organic. The baskets that they were using for their lettuce didn't permit them to do that. So we worked with them to develop baskets similar to what's shown on the screen here. We worked through a series of about 10 iterations involving about 16,000 baskets that we produced to make sure that we were able to manage the growth cycles, be able to deliver the organic requirements that our customer required, as well as optimizing the growth cycles. And through those efforts, we're able to provide over a 30% increase in produce yields, along with a reduction in growth time. And this is really remarkable. I realize that there may not be a whole lot of agricultural folks on the call, but we did 10 design iterations of 16,000 baskets, and we did that over a period of 90 days or so. We were able to basically test at scale, and that was remarkable for us in order to be able to optimize the product design and optimize the results. We found results that we would have never expected. And that had we been injection molding these parts on the second or third or even fifth iteration, I don't think that we would have been able to uncover the type of headroom that we found in terms of positive results. So to date, we've done something like 25 or 30,000 baskets in production. And this shows an image here of what some of that produce looked like growing on the aeroponic panels. We utilized additive for this all the way through to the growth stage, growth and maturity stage of the product life cycle. The other interesting thing about this project is that we were able to achieve such remarkable results in terms of produce output that we uncovered another market opportunity with a completely different type of produce than what our customer was growing. Something that was a much higher profit for him. So we uncovered a whole new market opportunity that we would have never been able to uncover had we not leveraged additive manufacturing. So from a production standpoint, we produced about 1,600 baskets per build. They were nested like solo cups. This shows a row of the baskets nested. And then this is kind of a neat photo that shows the baskets in the print process. So this is probably halfway through one of those rows as the parts were being printed. And this was being done in the multi-jet fusion machine using nylon 12. And these photos show some of what it's like for the parts when they come out of the machine. The photo in the upper right shows the baskets still nested in the build unit, and you can see that they're caked in powder. And then the photo below that shows the stack of parts that have been retrieved from the build unit that still need to go through post-processing. As we were going through our post-processing exercise, we uncovered opportunities to build in handling fixtures basically into the parts, so that when you pull a row or stack of parts out, they have built-in carrying fixtures to help simplify the post-processing.
Hey, Carl, I have a question here from Paul asking about the time it takes to clean the parts. Is this a time-consuming, or
It can be. Every project is a little bit different. These are pretty extenuating circumstances because there are so many parts and they're caked with so much powder. When we take a project like this on and we're in a production type phase, we'll actually develop the downstream process to semi-automate the cleaning of the parts. If you were to try and manage these parts with just a standard hand style bead blaster, it would take an extraordinary amount of time. It would take longer to post-process than it would to print. So what we'll do in these type of situations is we just develop the process to streamline that. And we've gotten these types of projects down where the post-processing really isn't that painful, but it can be if you don't have the infrastructure in place.
Thanks, Carl.
Robin, I know that we're getting close to our time here. I think you said that we had got a hard cutoff at 2 o'clock.
Pretty much. What we should do now is, I was really entertained by what you're showing. I mean, this is valuable information, and I'm sure there's a lot of questions out there. So what I wanted to do was kind of take the last 3 to 5 minutes and set it aside to address any questions and answer anything that the audience might want to throw our way. Feel free to drop in a question or two at any point.
Question just came in. Are we helping with COVID? We are helping with COVID. This additive, and I'm sure everybody on the call has been in tune with the news. additive manufacturing is a perfect technology to be able to respond quickly to things like COVID. We have been developing tailored solutions, whether it's masks or shields, to particular industries and customers. We're able to go from essentially design to production overnight. So yeah, the short answer is yes. And it's neat to see additive manufacturing coming to the call of duty.
Hey, Carl, I have a question that just came in from Cameron, and he's wondering about your post-processing capabilities. Could they send jobs to you to control surface finish? Is that something that you have capabilities to do in-house?
Yes, we are. We will typically post-process parts that we produce. Sometimes we've got customers that we've got great relationships with that have equipment, and they will send us parts to help them from a plating or finishing or painting standpoint. So we do help some of our customers with that.
And it looks like there is another question that came in about sterilization. How easy is it to sterilize HP material?
Very easy. A lot of the parts that we're producing today in response to COVID are being sterilized with the radiation as well as the heat method. The name escapes me, but they are able to be sterilized with all of the most common sterilization methods.
Great, thank you. Those are the only questions I have.
Figures we're a little bit of time here. I'll just share a couple of the images that I had on the next couple slides showing the pack of the masks. There's several different mask designs that are out there. We developed our own mask design that allowed us to pack them extraordinarily tight so that we can improve the production output. And if there's an Achilles heel of additive manufacturing, it's that it's not as fast as injection molding, but there are tricks to help improve output. So those are areas that we focus on.
Great. Well, thanks so much, Carl. I really appreciate everything that you've done for us today. I mean, this is some great information. Guys, this is you have about a minute left to kind of drop in a couple questions for Carl and the group. While we're waiting for those questions to come in, I'm going to go ahead and just thank everybody for joining today. Hawkridge Systems, obviously we have many locations. We have over 21 locations and we're continuing to grow. One of the things that we're really able to bring to the table, especially with Carl's group, is we can sustain and support their technology so that they can run 24 hours a day if needed. We offer a lot of different technologies here: HP, Markforged, scanning technologies, and we have about 9 dedicated locations to additive manufacturing throughout the United States and Canada.
And we appreciate your support, Hawkridge. As we continue to grow as well, we wouldn't be able to do that without you helping us run 24 hours a day. So thank you.
That being said, thank you guys and have a great rest of the day.